So linear algebra is primarily about, in the beginning, it's about systems of linear equations, like the ones that we just looked at in the readiness check. Right? The system that we looked at in the readiness check assignment generally consisted of two equations and two unknown variables, an x and a y, and two equations that bind to them. Right? And the fact that we have exactly as many variables as we had equations in those examples seems meaningful. Right? That those are typically the kind that we study when we first study linear systems. As it turns out, those are going to be the ones that generally give us the best chance at having a unique one and only one solution. But part of the story of this first chapter is going to be to bend those rules a little bit and say, well, what if we have more variables than we have equations? What if we have fewer variables than we have equations? What can the solutions of linear systems look like if it's not just a single unique solution or no solution? What are the other options? And how can we describe those other options? When we have systems that have infinitely many solutions, like the one that we just looked at on the readiness check, how might we be able to describe the set of all solutions to that linear system? So those are the kinds of questions that we're going to get into in Chapter E. And we're going to do that, first of all, by building some mental flexibility for us to think about linear systems of equations in three distinct perspectives. The first one is just as that list of equations that we're sort of used to. The second framing is going to be to think of them as what we call vector equations. So we're going to get a brief introduction today to vectors, which in a very real sense, vectors are the main objects of study in linear algebra. You'll notice that we have the longest chapter in our text is the chapter called vector spaces, because there is a whole lot to say about the properties of vectors. And then the third frame that we'll look at it in is in the frame of what's called an augmented matrix. What you might notice if you do enough of these linear system calculations is that when we do all of these calculations, the x, the y, the plus sign, the equal sign, all of that stuff just sort of stays put. The only thing that we're really doing is we're twiddling around with the coefficients, just the numbers, right? And so one might expect that we could, just by keeping track of those numbers, do all the same work that we're doing with these equations. And that's what the augmented matrix perspective kind of puts into a more concrete fashion. It says, well, let's just write the numbers, 12, negative 24, 54, negative 12, 24, and minus 36. And let's just do arithmetic on those numbers instead. And when it's convenient, we'll remember that that actually stands for these equations, and vice versa. But we can do all the same work in any of these three different perspectives. And so our job is going to be to gain some flexibility and familiarity with each of these different perspectives on what a linear system of equations is really telling us. So first of all, when we say the word linear, I mean, this is kind of what makes linear algebra, right? We are very rarely in this course going to see an exponent on a variable, right? There aren't going to be very many x squareds running around in our course. We will have occasion to see polynomials, but they're going to wear a very different hat and play a very different role in this course than they do in, I don't know, calculus. For the most part, the kinds of equations that we're interested in studying are equations in which my variables, which if I have a lot of them, I might use subscripts to denote them, like x1, x2, up to xn, are not going to be raised to any power higher than 1, right? And they'll have coefficients in front of them that are just real numbers. Maybe complex numbers, but probably not for our course this semester. And so we just have a sum of multiples of those variables on one side of the equation and a constant on the other side. So that's what we're going to call a linear equation for our purposes. And when we say a solution of a linear equation, what we mean is a list of x values, x1, x2, up to xn, that actually satisfy this equation. And we can think of that as n different numbers, but it's also just as well that we take all n of those different things and package them all up and wrap them into a box between a pair of brackets and call it a Euclidean vector. So here is the first vector that we're getting the privilege to meet this semester. And again, a solution just means that when I plug these values in for the x's in my linear equation, that we actually get a true statement, right? That it equals the right-hand side. So those are the kinds of equations that linear algebra is concerned with. And so again, when we have only 2 or 3 variables, usually we'll just fall back on x, y, or x, y, and z as their names. But we use the subscripts particularly to give us a easier on the eyes alphabet of variables if I have a lot of them to work with. And so a system of linear equations is nothing more than a bunch of these things, and a solution is going to be any vector of real number values that satisfy all the equations in this system. And so what we can do is speak of what's called a solution set. It's the set of all Euclidean vectors that satisfy all of the equations in our system. So when we say the solution of a linear system, we have to be really careful that the word the doesn't overdetermine the problem, because very often a linear system of equations will have more than one solution. And so it's going to be on us to find a way of describing the entire set, the whole universe of different possible solutions to a linear equation when there are more than one. Also, it's really, you'll see this in most linear algebra textbooks, that especially when we start thinking about vector and matrix forms for these systems, that we want to write them in ways that line up the common variables above one another. So all the x1s are lined up above the x1s, the x2s above the x2s, and so forth. And if there is a missing variable, we just leave a blank space there. That's really going to help when we start to convert these into vectors and matrix forms. So just as you're writing these things down on your paper, this is a good habit to get into to avoid making silly little copy errors along the way. So vectors not only play a role in describing the solutions of equations, they also play a really important role in describing the system of equations itself. So if we start out with the system like the one here on the bottom of the screen, x1 plus 3x3 is equal to 3, 3x1 minus 2x2 plus 4x3 is 0, minus x2 plus x3 is minus 2. I can also write this as a system of, as a single vector equation. Again, just by taking these numbers, the coefficients of the variables, and just plucking them out of that equation, sort of like factoring out the x1 and factoring out the x2 and factoring out the x3, and packaging all those coefficients into vectors in their own right. So that this equation up here, if I multiply x1 by this vector, I get 1x1, 3x1, 0. If I multiply x2 by this vector, I get 0, negative 2x2, negative 1x2, and then x3 likewise. And if I add those vectors together, I'm just adding them one component at a time, right? So I add all the first components together, I add all the second components together, and the third components together, and my right-hand sides are also packaged into a vector. So we can view any linear system of equations as a question about these vectors, these four vectors, 1, 3, 0, 0, negative 2, negative 1, 3, 4, 1, and 3, 0, negative 2. And this is a really important and understated point, and we're going to come back to this over and over and over again, especially in the chapter on vectors, that what we're really doing when we're trying to solve a linear system of equations is we're really asking, is there any choice of the real numbers, in this case x1, x2, and x3, such that that many multiples of this vector, added to that many multiples of this vector, added to this many multiples of that vector, actually gives us this vector. It's like, is there a combination of these three vectors on the left-hand side multiplied by some scalars and added together that equals this vector on the right-hand side? And so the benefit of this is, instead of thinking of my system of equations as three separate things, now I'm kind of thinking of it as a single equation, right? Is there some combination of these three vectors that produces the fourth? Right? So this is a really valuable way to think about what linear algebra is. And it is also what is going to ultimately give linear algebra its flexibility and its power. Because as we'll see when we start chapter V, vectors can be a lot of things. Not every vector is a point inside of XYZ space or something. We can consider polynomial functions as vectors. We can consider, JPEG images stored on our computer as vectors. We can consider, sine and cosine functions as vectors. We can consider electrical signals that we're trying to process as vectors. And because of that, the tools of linear algebra are going to give us the ability to say, well, can we find some combination of these polynomials which adds up to this polynomial? Can I find some combination of JPEGs that adds up to this JPEG, right? So this is where linear algebra really gets its flexibility, because there's so many different kinds of vectors out there in the world, and every vector equation is just one of these linear systems. And if we know how to solve linear systems, we then know how to solve these vector equations, because they're exactly the same thing. So a little terminology, just to set the stage, that a system that has no solution at all is called an inconsistent system. So if we say inconsistent, that means that there is no choice of my variables that makes all the equations true. And in every other case, if a system has any solution at all, we call it a consistent system. So its solution set is non-empty in that case. Now, this is a bit of a... If I were writing this book, and I don't like to second guess the authors because I enjoy them very much, if I were writing this book, I wouldn't give this away quite so soon. I'd want to make us work for this. But this is kind of an interesting fact that we are going to get sort of a good justification for as we move along. And that's that every linear system is either inconsistent, so it has no solution, or it is consistent with a unique solution, so there's only one choice of my variables that balances all the equations, or if it has more than one solution, it must have infinitely many solutions. So those are the only choices for how many solutions a linear system has. None, one, or infinitely many. All right, there is no in between. There's no linear system that has 3 solutions and only 3 solutions, right? So these are the only options. They're the only ways to do what we're trying to do when we solve a system. So here's the first activity that is going to feel an awful lot like the last question on the readiness check, I think. That every inconsistent linear system is discovered. We discover that inconsistency by finding a logical contradiction, a statement which we have collectively agreed not to accept as true. So let's take no more than 5 minutes with your group to take a look at this first activity, 1.1.1, and find a logical contradiction out of this system so that you can argue that its solution set is empty. And when you write up your responses, my first recommendation is to write up your responses in a way that will be useful to you when you read them later while you're studying for a quiz or an exam or something like that. So try to show your steps and explain your work, and do all of that work inside of your Google Drive folder. So this is the 1.1 E1 activity inside of that, and it's the first one of the activities on that page. So all 3 of your teams discovered what you needed to about this. One of the sort of underhanded goals, I think, of this activity is to get us used to using subscripted variables. So instead of x sub 1 and x sub 2, we could think of them as x and y. But this just, is starting to build those notational muscles for us a little bit. And so what all of you found was that if you do the elimination process on this particular system, that you end up with a logical contradiction in the form of an equation that looks like 0 equals 16, right? And as long as we all agree among ourselves that 0 is not equal to 16, then that means that there is no x and y that is going to satisfy both of these equations. So that is the source of the logical contradiction in this problem. I also saw one of the teams, I think it was team 1, went in and did a graph of these 2 equations in Desmos, which is a really good tool to use. I use it all the time in my multivariable calculus class, as a couple of you know. But if we go into Desmos and we type in those 2 equations, minus x plus 2y, and I think in Desmos we have to use x and y instead of the subscripted variables, is equal to 5. And the other equation was 2x minus 4y equals 6. Then sure enough, we find out that these 2 equations describe lines which are evidently parallel. So they have no intersection point. Can we think, by the way, of another way that we could tell from the equations that these 2 lines are parallel? Like when we first learn about parallel lines in analytic geometry, what is the telltale sign of parallel?
I mean, like you're gonna have, if you put it into slope-intercept form,
okay,
you're gonna end up having the same slopes.
Yes, parallel because these 2 lines have the same slope. So if we did the work to find the slope-intercept form of these equations, right, just solve each one of them for y. So I would add x to both sides here, and then divide both sides by 2. So my first equation, whoops, is y equals 5/2 plus 1/2 x. So there's the first one, and then I do the same work on the second one, subtract 2x from both sides, and then divide both sides by -4, so that 6 divided by -4 is going to be -3/2. -2 divided by -4 is going to be +1/2. And so that equation is y equals -3/2 plus 1/2 x. And sure enough, as you said, those 2 equations have the same slope, namely 1/2. So we could have seen that using the slope-intercept form. But one of the fun things that we do in linear algebra, right, is that we're going to come up with other ways of saying and discovering the same things. And so in the original system, what might be another way of understanding why it was that when the x's canceled, so did the y's? So you ended up multiplying the first equation by 2, right, in order to do that cancellation. And when you did that, the same proportionality that existed in the coefficients of x also existed in the coefficients of x2, the y's, right? So the left-hand side of the second equation was entirely a multiple of the left-hand side of the first equation, right? The second left-hand side is just -2 times the first left-hand side, right? And so that is another telltale sign, just using the coefficients, right? The second row of coefficients is a multiple of the first row of the coefficients. So when we start to repackage these systems as augmented matrix equations, we can speak of things like the rows of numbers that consist of the coefficients of these equations and look for relationships between those rows of numbers. Instead of computing a slope, which in the two-dimensional case is a single number that kind of represents that proportionality. But that idea of slope is an idea that's difficult to take into higher dimensions. If I have 3 variables or something, then the meaning of the word slope is entirely unclear. This is actually one of the things we looked at in multivariable calculus this week. If we want to describe a line in 3-dimensional space, we can't use a single number like a slope. We have to use something like a vector to describe the direction of a line in 3-dimensional space. So that's going to be kind of the mental gymnastics that we're going to have to do.